In 1897, a metallurgist named Hiram S. Maxim presented a paper to the Royal Society describing an alloy sample recovered from a demolished exhibition hall in Vienna. The metal fragment weighed less than 1/5 of what its volume should have allowed. The sample was logged, catalogued, and then quietly removed from the archive within 18 months. No explanation was recorded. No subsequent reference to it appears in the Society's publications. When I requested access to the original sample log, I was informed the relevant pages had been damaged by water and were illegible. Across 3 continents, photographs from the late 19th century show structures that seem impossible by modern engineering standards. Massive domed roofs, intricate metal frameworks, towering spires, and all allegedly constructed in months for temporary World's Fairs, then dismantled and erased. Engineers today cannot explain how such structures could have been raised so quickly, nor how the materials could have been transported with the infrastructure of that era. A single iron girder of the dimensions shown in these photographs would require multiple freight cars and specialized lifting equipment that did not exist at the time. The official record insists these were simply iron and steel. Scattered documents, patent applications that were never granted, and laboratory notes that survived in private collections suggest something else. A metallurgical process that produced alloys of extraordinary strength at a fraction of conventional weight. These sources are fragmentary. They contradict each other on specific details. Yet they all describe the same fundamental phenomenon, metal that should not have been possible with the technology of the time. If such a process existed, where did it go? And why does no institution acknowledge it today? What follows is documentation. It is evidence gathered from archives, analyzed by experts, and presented without conclusion. I began this investigation where most histories of 19th century industry begin, with the Bessemer process. The year was 1856. Henry Bessemer discovered a method to convert molten pig iron into steel by blowing air through it, oxidizing impurities and producing a stronger, more workable material. Within 2 decades, this process had transformed construction, shipbuilding, and transportation. By 1900, steel production had become the backbone of industrial civilization. In 1870, the global steel production was measured in thousands of tons. By 1900, it exceeded 25 million tons annually. Cast iron was brittle. It could support vertical loads but fractured under tension or impact. Wrought iron was more malleable, but producing it required skilled labor and time-intensive hammering. Steel solved both problems. It could be cast into shapes, forged into beams, and riveted into frameworks. The great exhibition halls, bridges, and civic monuments of the late Victorian era were built from these materials, hauled by rail and assembled with cranes, scaffolding, and enormous crews of workers. Construction took years, demolition took months. Everything had mass, weight, and resistance. This was the age of heavy industry. Mass was synonymous with strength. I examined engineering manuals from the period, in texts from the 1880s and 1890s that outlined the structural limits of these materials. A cast iron beam supporting a domed roof required certain dimensions to bear a given load. The calculations were precise. The tolerances were known. I found these specifications repeated in university archives, industrial records, and municipal building codes. A truss spanning 60 feet required members of a certain thickness. A column supporting a 5-ton load needed a minimum cross-sectional area. These were requirements derived from material properties that had been tested repeatedly. As I continued reading, I noticed something. In private correspondence between engineers working on World's Fair pavilions, there were occasional references to structural behaviors that did not align with these published standards. A letter from 1893, written by an architect overseeing construction in Chicago, mentioned roof trusses that appeared too slender for their span. He described consulting with the fabrication contractor, who assured him the materials had been tested and certified. The architect expressed uncertainty, but did not pursue the matter further. His letter ended with a single line: "The roof was installed without incident." I found no follow-up correspondence. The architect never mentioned it again. If the materials conform to known metallurgical properties, why would an experienced engineer express doubt? The evidence suggests that what was being used in certain high-profile projects did not entirely match what the official technical literature described. I found similar remarks in journals and committee reports from Berlin, Paris, and Vienna. Always brief, always unresolved, always followed by confirmation that the structures stood as designed. In one instance, a municipal building inspector in Vienna noted that a pavilion roof appeared to violate load-bearing calculations, but passed inspection after the contractor provided certification documents. The inspector filed his observation in a marginal note. No investigation followed. I turned my attention to the structures themselves. The 1889 Exposition Universelle in Paris featured a central gallery with a vaulted glass roof, spanning nearly 300 feet. Contemporary accounts describe its construction as rapid, completed in less than 6 months. Photographic evidence shows minimal scaffolding. The framework appears remarkably thin in relation to the span it supports. When I compared these images to photographs of similar structures from the same period built using conventional methods, the differences were striking. I consulted with a structural engineer who specializes in 19th century architecture. I provided him with the dimensions and photographs. He performed load calculations based on the assumption that the structure was made from conventional wrought iron or steel. His conclusion was unambiguous. The proportions were not feasible. For the roof to support its own weight plus wind loading and the mass of the glass panels, the members would need to be at least twice as thick. Otherwise, the structure would have deflected visibly or collapsed during assembly. He added that even with modern steel, on achieving such a span with members of that thickness would be considered aggressive by contemporary standards. Yet the photographs show no deflection. The roof stood for the duration of the exposition and was dismantled without reported structural failure. No contemporary observer remarked on any visible sagging or distortion. Visitors walked beneath it. Dignitaries held ceremonies under it. The French government awarded medals to the engineers responsible. If the structure had been visibly unstable, someone would have noticed. I examined similar cases. The Palace of Mechanical Arts in Chicago, 1893. The Imperial Pavilion in Vienna, 1898. The Brussels International Hall, 1902. In each instance, the documented construction timelines appear incompatible with the logistical and material constraints of the era. Transportation records indicate that the tonnage of steel and iron shipped to these sites was insufficient to account for the structures that were erected. Municipal freight logs show discrepancies between expected material volumes and actual deliveries. In one case, customs records for iron shipments to a construction site were 40% lower than engineering estimates for the completed structure. One explanation could be incomplete record keeping. But I noticed a pattern. These discrepancies appear exclusively in records associated with major exhibition buildings constructed between 1875 and 1910. Factories, rail stations, and residential projects from the same period show no such anomalies. The gaps are specific, they are consistent, and they coincide with a window of time in which something unusual was occurring in the field of metallurgy, something that left almost no formal documentation. When I requested access to construction records for 3 separate World's Fair buildings, I was informed that 2 had been lost in archive fires and 1 had been transferred to a repository that no longer exists. I began searching patent archives. Between 1870 and 1915, I found over 24 applications describing processes for producing lightweight metallic alloys. These were not filed by a single inventor or institution. They came from independent metallurgists, industrial chemists, and small fabrication firms scattered across Germany, France, England, and the northeastern United States. The applications were filed in different languages, using different technical terminologies, yet they described remarkably similar outcomes. Most described heat treatment methods involving controlled atmospheric conditions, processes that required maintaining specific gas mixtures during the tempering phase. Several referenced vibrational or acoustic energy as part of the forging process, a technique that has no modern industrial equivalent. One application, filed in 1887 by a metallurgist in Dresden, outlined a method for infusing gaseous compounds into molten metal under pressure, then rapidly cooling the material to lock the internal structure into a crystalline lattice of unusual density. The inventor claimed this process reduced weight by 30 to 40%, while maintaining or exceeding the tensile strength of conventional steel. His drawings showed elaborate apparatus involving pressure vessels, acoustic chambers, and precisely timed cooling systems. I examined the outcomes of these applications. The majority were rejected. Patent offices cited reasons such as insufficient demonstration of feasibility or lack of supporting test data. Some were withdrawn by the applicants before examination. A small number were granted but never renewed, suggesting the inventors either abandoned the work or were prevented from continuing. I traced the fates of the inventors. In several cases, they disappeared from public and professional records within a few years of filing. One metallurgist, whose work appeared frequently in trade journals before 1890, published nothing after 1892, and left no record of employment or relocation. His name appears in one final document, a death certificate filed in 1894, listing cause of death as accidental drowning. 2 patents were placed under industrial secrecy provisions, a legal mechanism typically reserved for processes with potential military application. Both involve methods for altering the internal microstructure of iron-based alloys through non-thermal means. The patents were sealed in 1897 and 1903 respectively. No subsequent documentation exists regarding their use or development. The inventors received no recorded compensation. The patents remain classified or were destroyed. I filed requests under Freedom of Information statutes in 3 countries. 2 were denied on grounds of national security. 1 was acknowledged but never answered. Multiple individuals, working independently, who pursued processes that aimed to reduce the weight of structural metals while maintaining or enhancing strength. These efforts were not coordinated, yet they converged on similar techniques. This convergence suggests that these inventors were not imagining a theoretical possibility. They were reverse engineering something they had observed or encountered. The official explanation does not fully account for why so many unconnected researchers would simultaneously pursue the same elusive goal unless they had all seen the same evidence, structures that should not have been possible with conventional materials. I turn to the technical details. What precisely were these inventors attempting to achieve? I gathered surviving laboratory notes, trade journal articles, and fragments of correspondence. From these scattered sources, a hypothesis began to form. The process was complex, but the underlying principle was straightforward. Alter the internal structure of metal to incorporate void spaces while maintaining the integrity of the load-bearing matrix. The process appears to have involved 3 stages. First, a base alloy, likely iron with trace additions of carbon, silicon, and other elements, was melted in a controlled atmosphere. The exact gas mixture varied between sources, but nitrogen, hydrogen, and argon were frequently mentioned. The purpose was to prevent oxidation while allowing certain gases to dissolve into the molten metal. One set of notes described maintaining a pressure of 3 atmospheres during the melting phase, with temperature held within a narrow range to maximize gas absorption. Second, the molten alloy was subjected to acoustic vibration. And one set of notes describes a forging apparatus that used tuned resonance chambers to apply specific frequencies to the material as it solidified. The frequencies were not arbitrary. They corresponded to the natural resonance of the crystalline structures forming within the cooling metal. The effect, according to the notes, was to align the grain structure in a way that eliminated internal voids and microfractures while preserving the larger gas-filled cavities. The inventor compared it to tuning a musical instrument, finding the frequency that caused the material to organize itself into optimal configuration. He noted that the process required constant adjustment as the metal cooled, tracking the changing resonance as the crystalline structure formed. Third, the metal was rapidly quenched, not in water or oil, but in a gas at low temperature. Conventional quenching introduces stresses and can cause warping. The gas quenching process described in these documents appears to have locked the internal lattice into a stable configuration that retained the gaseous compounds within the structure itself. The result was an alloy with a cellular microstructure, pockets of trapped gas within a metallic matrix. The load-bearing pathways remained solid, but the bulk volume contained significant empty space. One inventor described the final product as resembling frozen foam, though with the strength of solid metal. I consulted a materials scientist. I described the process without mentioning its historical context. His response was immediate. Such a material would have a significantly reduced density. The trapped gas would lower the average weight while the metallic matrix maintained structural integrity. He noted that modern metallurgy produces metal foams using similar principles, though these are typically used for impact absorption rather than load-bearing construction. He added that achieving this effect in iron or steel would require precise control over temperature, pressure, and timing, conditions difficult to replicate even with contemporary equipment. When I asked if such a process could have been achieved in a 19th century foundry, he paused. Then he said it would depend on the skill of the operator and the sophistication of the equipment. It was not impossible, just improbable. If the process was theoretically sound, and if multiple inventors were attempting to refine it, why did it vanish? The evidence suggests that at least some of these efforts succeeded. The structural anomalies, the architectural impossibilities, the missing tonnage, all point to the existence of a material that modern industry does not produce and does not acknowledge. I examined what happened after 1915. The great exhibition buildings began to disappear. Some were described as temporary structures, dismantled as planned. But the scale and speed of the demolitions were unusual. Entire pavilions, some built to serve as permanent cultural institutions, were torn down within years of their completion. In several cases, demolition occurred despite public opposition and offers of preservation funding. The Machinery Hall in Chicago stood for only 3 years before demolition began. The Vienna Exhibition Palace was razed in 1919, less than a decade after its inauguration. Municipal records cite structural concerns, but no engineering reports substantiate these claims. I traced the disposition of the materials. Standard procedure for large demolitions involved salvaging and reselling structural components. Iron and steel had commercial value. Scrap dealers paid by the ton. Yet in multiple instances, the demolished materials were not resold. Municipal records indicate that the metals were removed from the sites and transported to undisclosed locations. Scrap dealers from the period made no mention of receiving shipments from these projects. In one case, a demolition contractor noted in a ledger that materials were collected by government representatives and no payment was issued. Around the same time, metallurgical archives underwent consolidation. University collections, industrial libraries, and patent offices transferred certain records to centralized repositories. Some of these repositories were later destroyed during the World Wars. Others were reclassified under national security provisions. I found references to transferred materials in administrative logs, but the contents of those transfers are no longer accessible. Requests for access are denied or redirected. In one instance, I was told the materials had been moved to a facility that closed in 1967. When I asked what happened to the contents, I was informed no record existed. Several individuals associated with lightweight alloy research left the field abruptly. A chemist who had published extensively on gas-infused metallurgy accepted a position with a government laboratory in 1919 and published nothing further. And another researcher, whose patent applications had been placed under secrecy orders, moved to a remote estate and ceased all professional correspondence. In at least 2 cases, obituaries appeared for metallurgists, who were later reported alive under different names. One was photographed at a factory in Pennsylvania in 1932, 13 years after his reported death. No explanation was provided. I do not assign blame. I do not speculate on motives. But I note the pattern. Within a span of 30 years, a body of knowledge appears to have been systematically removed from public access. The structures that embodied this knowledge were demolished. The individuals who possessed it were silenced or disappeared. The records that documented it were seized, reclassified, or destroyed. What remains is absence, an absence so complete that most historians do not notice it is there. When I presented these findings to an academic colleague, he suggested I was seeing patterns where none existed. But he could not explain why so many records vanished during the same narrow window of time. I returned to the present. I examined the capabilities of contemporary materials science. Modern aerospace engineering produces titanium alloys, aluminum-lithium composites, and carbon fiber reinforced polymers. These materials achieve impressive strength-to-weight ratios, yet none approach the properties suggested by the 19th century evidence. I compiled data from aerospace manufacturers, construction firms, and materials research laboratories. We have made progress, but we have not recovered what appears to have been lost. Carbon fiber, for instance, offers tensile strength comparable to steel at 1/5 the weight. But it is not a metal. It cannot be forged, welded, or cast. It requires specialized manufacturing processes involving high-temperature ovens and precise layering techniques. It is prohibitively expensive for large-scale structural applications. The great exhibition halls were built with materials that could be fabricated, transported, and assembled using the technology of the 1890s. No modern composite meets those constraints. A carbon fiber beam costs hundreds of times more per unit than steel and requires climate-controlled facilities for production. Metal foams exist, but they are weak. They absorb impacts well, but they cannot bear significant loads. They are used in automotive bumpers and packaging, not in bridges or roofs. Advanced alloys like titanium aluminide offer high strength at reduced weight, but they require temperatures exceeding 1500 degrees Celsius and pressures far beyond what 19th century foundries could achieve. The gap between what we can produce today and what the evidence suggests was produced then remains unexplained. Modern materials science has pursued lightness through composites and exotic alloys, not through the modification of conventional metals. I spoke with an engineer who has worked on historical restoration projects. I asked him about the materials used in the few surviving structures from the period. He told me that when original components are analyzed, they sometimes show microstructures that do not match contemporary manufacturing processes. He described finding gas pockets within iron beams, in crystalline patterns that suggest non-standard cooling, and alloy compositions that deviate from documented formulas. These anomalies are noted in internal reports but are rarely published. They are treated as curiosities, not as evidence of a lost technology. When I pressed him on why these findings were not investigated further, he said there was no funding for research into obsolete methods. If the process existed, and if it produced materials superior to what we use today, why was it abandoned? The standard explanation is that it never existed, that the structural anomalies are misinterpretations, the patent applications were failures, and the archival gaps are coincidental. But this explanation requires us to dismiss a large body of circumstantial evidence. It requires us to believe that multiple independent engineers, working across different countries, all made the same observational errors. It requires us to accept that a series of demolitions, seizures, and disappearances happened without coordination or purpose. I cannot prove what happened. I can only present what I have found. The official narrative of metallurgical history is incomplete. Something was pursued, developed, and then erased. Whether it was suppressed deliberately or lost through neglect, the result is the same. We no longer possess the knowledge to replicate it. This is not progress. This is forgetting. And if we have forgotten this, what else have we forgotten?